All right, hey guys, it's Sharky. We're going to do a little review on the topics that we need to start the year off. We actually start the year off talking about something called fluids, but it's really all just Newton's laws, forces, energy, and work. So here we go. All right, here's some things that you're going to need to know or you need to remember. Facts about force. I'll write some of these things down in your notes if you need them. Important stuff. We have contact forces and we have field forces. Gravity, of course, is an example of a field force. There you are. Oh yeah, I heard Chuck Norris got the coronavirus, and subsequently the virus has to quarantine for the next 14 days. All right, Newton's first law, sometimes called the law of inertia. I call it the seatbelt law because it's the reason why we wear seatbelts in cars. Interestingly enough, a lot of the people who are resisting wearing masks are using the same arguments, using the same arguments for the same arguments as those people used to not want to wear seatbelts, which I think is kind of funny. Here you go. So this equation right here is one that we're going to need. Inertia. You need to know what that means. Inertia is really synonymous with mass. Mass and weight are two different things. And if you guys remember, if you had me for last year, you knew that I fought tooth and nail to get you guys to understand the difference between mass and weight. They're different things. Okay? To calculate weight, it's a calculation. You have to actually calculate it. And gravity, or a gravitational field, is needed in order to have weight. You have mass all the time. I can check you out in the space, and you're still you. You have mass. That's the thing. Newton's first law says an object in motion remains in motion. You can read it. There it is. Okay? This is not readily apparent here on Earth, because usually things stop, and they stop because of, yes, friction. And so we talked about, in my classes, we talked about why when we have ice and snow, we don't go to school. It's because of lack of friction. Well, that little picture I have up there. You have to know how to draw free body diagrams. If you've dumped all this, you're going to have to review in your notes from last year. FBDs are a big part of AP2. And so we've got to remember how to do this stuff. You need to know the differences between what is weight, what is tension, friction, right? This is called an Atwood, and you guys hopefully remember how this works, where this part will drop down, this part moves across like that. We could draw one FBD for this weight and one for this weight, and that's a good practice to do. How many forces are acting on this weight on the table right here? Let's say that there is friction between the table. And how many forces would be acting on this one? This hanging one right here. Let's say that there's no air, so there's no air friction. How many forces are acting on this hanging weight here? And there you go. Those should be your forces acting on this block, forces acting on that block. Boom. Oh yeah, things on hills. Oh, this was really something when we had to do this in the fall. How many forces? Well, everyone can tell me there's a downward force here. I had all my students trained. This downward force is the force due to gravity, right? Called weight. How many other forces? Let's say that there is friction. Let's just say that there is friction between this box and the hill. How many forces could we draw? How many real forces? Go back. There we go. Those are all your real forces right there. There are three. This is called the normal force, if you remember this. Yes? The normal force is perpendicular to the surfaces in contact. Frictional force always acts in the opposite direction of the intended motion. So if this box is intending to move down the hill, then friction acts up the hill. And of course, there was a question that, well, the box moves this way down the hill. So why isn't there a force pulling you down the hill? Why isn't that happening? What's causing it to go down the hill? It's this one, right? It's gravity. Why is there no force pointing that way? If you remember from the fall, there actually is. This makes a right triangle. You can see that right triangle there. And so there's actually component forces here. There's a force going this way and there's a force going down. They're components, so they're pieces. All right, here's an example problem. And it's already got some answers on it. Force of friction. We're talking about friction here in a minute. And here's the weight if you have the box. And there are all the forces acting on the box. These are just example problems that you can see. This is a tricky one because the box is actually being pulled along the ground, but there's an angle here. It's actually being pulled because the person is upright and they're pulling, right? But it's moving along the ground, so there's actually a right triangle right here. And we'd have to break that up into those pieces. The normal force is going to be less than you think because the person pulling is actually pulling up. There's an up force here, pulling up. And there are component forces. There's our right triangle, right? This force in the X is the only actual force causing the box to move along the ground to the right. This upward force here is the person pulling up. This force plus this Fn, this normal force, these two forces, equal this force going down. That's the thing. What if something's not at equilibrium? Well, there you go. The forces are not balanced. The thing will speed up. You will feel an acceleration. Here's Newton's second law. Basically, it's this equation, A equals F over M, or F equals ma. Second law. Some examples. Here's an example. What are all the forces acting on this thing? There they all are. There's all the work done for you. No fun. So there you go. You got to be able to draw forces. You got to be able to know which way are the forces going. You have to know some of these equations. F net equals ma net, and A net causes an F net. So just know. I said that a lot last year. Here's an example of an Atwood. You would have to draw a free body for this one and a free body for that one. What I do when I'm doing this is I figure out what is my equation for this one, what is my equation for that one. I then take the two equations and I add them up, and it looks like a big nasty mess. This is something I probably have to make a video showing how this works. I may have to do that. Dadgummit. It's frictionless, so there's no friction force going this way. So this has three forces acting on it. This has two, right? This equation right here looks like your total equation, right? M2G is this force going down, M2G minus T, so this part is your equation for this one, right? So this is this guy. For this one, this Fn and this M1G, they cancel out, so all you have left is tension. So this equation here is for this guy. If you guys remember, I always say winner minus loser, right? So this block goes down. This is my winning force. This is my losing force. Winner minus loser. So winner minus loser equals M2A. This is M2. Here's M1. There's only one force. It's just tension. So tension is the winner equals M1A. And we add these two equations together. And that's what they're doing here. M2A plus M1A is on this side. The T's cancel, and you got M2G, and then you create this equation you can solve for things. That's how I always learned how to do that. If you guys remember, we can graph stuff. Graphing is a thing. I think this is really showing us that if you can graph these things, if you graph F and A, F on the y-axis, A on the x-axis, the slope ends up being your mass. Because what's F divided by A? It's M. That's Newton's second law. Finally, work, energy, and power. We're going to start the year talking about this stuff. You got to know what work is. Energy. These are all the different types. Energy and work are really the same thing. Work equals F times displacement, Fx. I usually wrote it FD in class. Work equals FD. It's actually FD cosine theta. It's a dot product. And a dot product is basically a constraint. And it means that if you're moving this way, if your displacement is this way, and then your force has to be that way in order for the work to be in the same direction. All these things are in the same plane, essentially. Are you doing work or are you not doing work? What do you think here? Which one of these are you doing work? Which one of these are you not doing work? See it in the box? Pushing or pulling up or down is not going to do any work in the x direction, so you wouldn't be doing work here. There is work happening here. I can't stand this, but negative work and positive work, technically work is a scalar, so there is no such thing as negative work. It just means that F and X are in different directions. Okay. So here they would call this, sometimes I would call this positive work. It really just means F and X are in the same direction. Here, F and X are in different directions. This confused people a lot last year. So if my F is my force is to the left and my X is to the right, how is that possible? How can my force be one way and my displacement be the other way? How is that possible? Can you think of an example? The example that I think of is coming to a stop. When the light turns red, we're supposed to hit the brake. And when you hit the brake, you still travel towards the light, but that braking force is actually in the opposite direction from the way that you're going. That's what your brakes do. And we're going to talk about energy in the next video that I make. And so these are just this is a lot of gobbledygook to explain to you how this equation comes about, but this theorem basically says is that when you do work on something, the kinetic energy of that thing changes, and that kind of makes sense. When you do work, things move, and when they move, the kinetic energy has to change. So if you kick a ball, you've done work on it, and the ball moves. Here's an example of a problem. Give that a shot. Good. This is a good term to know. Equilibrium. Finally, frictional forces. You got to be able to calculate friction. You got to know what friction is. Friction is the imperfections between surfaces. If you guys remember, we had two types of friction, static and kinetic. There's really only one equation for friction. Friction only depends on two things, normal force and something called mu. If you guys remember what mu is. Mu is this weird looking symbol here. N, I usually call it Fn, is the normal force. It's the same equation. It's independent of area. It's an